Everybody say hi.
Hello.
This is a section that we spent a fair amount of time on last year. And because we spent so much time on it, the reason we spent so much time on it is so that this year we could just kind of look at it and go, yep, I get it. I know why that does what it does, because we did all the nuts and bolts stuff last year. This is kind of a reminder about that. The goal of this is to be able to just look at equations and know stuff about equations. A minute ago we were talking about one of the, what does putting a -3 inside the function do to the graph? And you just know what that does and you have an idea of what the graph looks like. People who are good at math, that's us, can just look at stuff and know answers. And we get there by doing the nuts and bolts. So the goal of this is to be able to take an equation, do something to that equation, and know what that thing does to the shape of the equation, so that we don't have to spend a lot of time thinking about that. So, quick reminders. There was a difference as to where the value is, as to how it affects it. Remember the idea of if I have a function and I put a plus c outside, or if I have a function I do a minus a number outside, what those do to it, versus what happens when you put the number on the inside of the function, and how does that change it? And the difference, of course, is something like this. If I had y equals x squared, if I put a plus 3 out here versus putting a plus 3 in there, that does different things to the function. And that's what we're trying to get at. Just be able to glance at it and go, that's what happens. So what happens in the first one? Plus c outside, let's assume c is a positive value. It's going to go up. What's going to happen in the second one when I put a minus c, again assuming c is a positive value? It's going down. This guy's going to go to the left, and this guy's going to the right. Up c, down c, left c, right c. Sounds like a Dr. Seuss book, doesn't it? One fish, two fish, red fish, blue fish. Did you? Up C, down C, left C, right C. Okay, so we have those down. So again, the difference is we're supposed to know what the parent function looks like. We know what x squared looks like. It's a parabola. And we know that that's not inside the function, that 2. It's outside the function, so it's going to affect the graph in the y direction, since it's not in with the x. And when it's outside the function, it does exactly what it says it's going to do. When it's inside the function, it does the opposite of what we think it's going to do. And the way that I remember that is, I know that the parabola of y equals x squared has a 0 at 0. Because when you put 0 into x squared, you get 0. Well, what number do I have to put in here to get 0? Is -2, which is why it shifts it to the left. And so once you kind of just get that pattern straight in your head, you don't have to think about it. When it's in with the x, it does the opposite of what you think. So that was just the translation stuff, shifting it over from one place to another place, just moving it. And the idea of translation is, like the foreign language, when you translate into another language, it's supposed to be the same when it gets to that new language, as opposed to these guys that actually change the shape. So this comes into what we call transformation. So we're changing the shape of the function, not just moving it. Again, making an assumption that c is bigger than 1, not only positive, but bigger than 1. What's this guy going to do to it?
Like it's a parabola, it's going to make it taller, narrower.
Pick.
Narrower.
Pick the other one.
Taller.
Taller. It's a vertical stretch. Now, with a parabola, a vertical stretch kind of sort of looks like it got skinnier, but that's not how it got there. When I take a parabola and make it taller, it looks like it's squeezed in, but technically that's not what happened. I'm going to give you a for instance here. If I have just a simple graph that does this, and that's f of x. And then I want to see what 2 f of x is. Every single value gets whatever that distance, double it, and that's the new point. Whatever that distance is, double it, that's the new point. That distance, double it, that's the new point. So it didn't get skinnier, it got taller. Now, what that looks like with a parabola, if I do the same kind of thing with a parabola, and every point gets whatever this distance is, make it taller. Whatever this distance is, make it taller. That stays 0. It ends up looking like this. It looks like it got skinnier, but it really got taller. Any point on the graph is twice as tall as what it should have been, or was. All right, what's this guy do? If the other one's a vertical stretch, it's shorter. It's a shrink. In with the x does the same or the opposite of what we think it's going to do. Opposite. So f of cx is going to get, well, first of all, it's in with the x, so it's going to affect the graph in the x direction horizontally, and therefore it's going to take and do it's going to shrink it. For example, sine of x. Sine of x looks like this, looks like that. How long does it take to get out to the end here? Yep. And so this guy, color, this guy is going to do the same pattern, but it's going to take half as long. So I'll get that. Because think about what happens here. When I put pi, this is pi, when I put pi into this equation, I'm getting the answer that occurs at 2 pi. So the 2 pi answer now happens at 1 pi.
Wait, isn't that a period?
It is in this case. Actually, the period for the sine is 2 pi, and you divide by this value, and that's the new period. Not everything is a periodic function. So with a division by c, horizontal big, or stretch as the case may be. Well said. Nice job. And then the last two, when the negative is on the outside, give me a better word. Reflection over the x-axis. And the other one, when it's in with the axis, it affects the graph in the x direction, which means now I'm reflecting over the y-axis. Now we don't, it's not like these are questions on a test, per se. But what will happen is, there'll be a problem that has an equation where something is going on to it, and you can get caught up in trying to figure out what the graph looks like. And I want you to be able to just glance at stuff and go, oh, that's a whatever, and be able to get on with the problem. And so this is just a little minuscule kind of thing that becomes important. Those are all the translations, transformations. Another kind of thing that we will do to graphs. Absolute value. First of all, what does x squared minus 4 look like? Describe it. Words.
The y-intercept is 0, -4, and it is a regular parabola.
See what you're about to say?
It's the parent function
Of
the parabola.
Of x squared. The parent function is x squared, and the minus 4 does to it is drops it down 4, right? Takes it down to 0, -4. But don't forget, absolute value is a piecewise defined function. Anytime you see absolute value, think piecewise defined. If the stuff inside is positive, then the absolute value of the stuff inside is the stuff inside. If the stuff inside is negative, then the absolute value of that stuff is the keyword opposite of. And so that's what I've done here, is I've taken the opposite of this stuff if the stuff is negative. If the stuff is less than 0, then take the opposite of the stuff. If the stuff is positive, the absolute value of 5 is 5 because 5 is positive. If the stuff inside is positive, you just make the absolute value signs go away. Yep.
So are you supposed to like solve that out and be like the x squared is 2 thing?
Yep. And so what I want to do is figure out where is this positive, where is this negative. So let me find out where this is equal to 0. Well, do a little factoring. I get these zeros at 2 and negative 2. And since we already kind of sort of know what this shape looks like, now this is way overkill for this problem if you know this stuff intuitively. But these are the zeros of the function. Now when I plug in, if I plug the number 0 into here, if I plug 0 into there and I plug 0 into there, I get negative 2 times 2, that's negative. So in between these 2 points, this function is negative. When that function's negative, you have to take the absolute value of it, you have to take the opposite of it. So this equation is the one I'm going to graph when I'm graphing in between those 2 points. Distribute the negative sign, I get negative x squared plus 4. Negative x squared, the negative outside the x squared, not in with the function, what's it do to the graph of x squared? Missed the first word. Reflects it over the x-axis. And then the plus 4 at the end shifts it up. So this graph is just that thing right there. Outside of the parentheses, outside of the 2 and, not parentheses, sorry, the boundaries there, the 2 and negative 2, this is positive. And if that's the case, I just use plain old x squared minus 4. X squared minus 4 is a parabola shifted down 4 units. There's my parabola shifted down 4 units. But the part of this that's there that's not supposed to be there is in here. Because that's where this graph is less than 0. And so I don't graph that part. Because I only graph this if this is greater than 0.
Right.
And in between, it's not greater than 0. And so this graph doesn't get graphed between the 2's, the negative 2 and positive 2. Now, the short of this is you draw your normal graph and just keep in mind that anything that's negative, the stuff that's down here that's negative, gets flipped over the x-axis. It becomes reflected over the x-axis. And you just kind of get this W shape.
Shouldn't you not have to graph the red, like the upside down parabola, because it's not less than 0?
And so when it's not, but it is less than, when I pick the number 0, and I plug 0 into this, if I plug 0 into there, I get 0 minus 4 is negative 4. Is negative 4 bigger than 0? No. Don't do that graph. When I plug in 0, I get 0 minus 4 is negative 4. Is negative 4 less than 0? Yes. Then graph that graph, which is the upside down parabola moved up after you distribute the negative sign. Graph 2 periods of that. pretend all those humps are the same height. Right? You see it? Anything that's negative, any place where this graph is negative, the absolute value would simply reflect it over the x-axis. And what you get are just kind of this bumpy ride. Pothole road.
But if wait. If x is less than 0, but on none of these x is less than 0, would that be on the opposite side?
This is so it would be the sine of x if the sine of x is less than 0, not x less than 0. The sine of x is less than 0, and then it's the so if it's the opposite of this would be greater than, and then it's the opposite of the sine of x if. So then you got to figure out, okay, where's the sine of x less than 0? Where is it positive? So the sine is negative in the second and third quadrants, right? When you do an angle rotation, not second and third, third and fourth, So that happens. So this is pi over 2. This is pi. So starting right here at pi, the sine would normally start to become negative, right? At pi, this would normally be where it starts being negative. And so this is first quadrant to here, this is second quadrant to there, third quadrant to there, fourth quadrant to there. And then it repeats. So I already talked about piecewise defined, how to write that. Glance at this in the book a little later on. They talk about the domain and of combining the functions. It's not a huge deal, but this is kind of, again, one of those little pieces of things that the more you can kind of get in there, the better. I'll do this a lot this year, where it's not a huge point. It's not like there'll be a question on the AP exam about this, or even for that matter, one of mine. But the people who spend a little bit of time, even though I'm not going to grade it or look at it or talk about it necessarily, read through this kind of a thing and kind of see what you can get in there. The more you can get in there, just the easier other stuff becomes, because you've got these background facts. So glance at what's going on in the book on that page. Take a look at that. So one of the things they do talk about is, remember in our rule of 4, we can look at equations, we can look at graphs, we can have a story about something, we can look at a table of data. We've done, this is kind of a combination of functions, like when you do f of x plus g of x. And you can do that algebraically, that's kind of simple. This is the same logic graphically. And just kind of want to take a second to talk about what that means, what that looks like. Remember what f of x is. F of x is the y value. So when I pick a number for x, 2, I plug 2 into the function, I get an answer that's a y value, and that tells me where, so if this is 2, that tells me where to plot that point. So when I say f of x plus g of x, what you're doing is simply adding up the y values. Well, the y value is a distance. How far is it from the red line up to where your graph is? That's what f of x is, right? So when you do a sum, all you're doing is adding the two distances. So at x, at this x value, this distance is f of x. And at x, oops, I only got one of them. That's because it didn't go up high enough. Get that one out of there. Oops, that one did. That black line is the function value of g at that point. That's g of whatever that x value is. So when it comes to doing f plus g, you literally just take the black one, right, and slide it up and add the two distances together. That's a point. That's the point on f plus g. And if you do that all the way across, pick another random point down here. You do this all the way across, and you'll get a collection of points that is the sum of f and g, etc., etc. So what I'm doing at any random point, I pick this distance and this distance, and if you add them up, you should end up, fudged it a little bit, fake it. It should end up on the line. Graphically, that's what happens when you do this. Okay? This, on the other hand, is a fairly significant concept. There will be some things we do this year that if you do not understand this notion of composite function, you will not be very successful in calculus. What does this tell you to do with these two functions?
I can,
Question first.
Well, question first.
Yeah.
What is the notation when it says like G, like dot, bob?
What does it like this? It's the same thing, and I don't know why they do that in pre-calc books, because you never see it in upper level books. But it's the same notation. So this means the same thing as that. So what does this tell you then?
You take the y value from, or the answer of the f of x function and plug it into the x of the g function.
But yes, so I take the answer of whatever f is and I plug it into the g. But what if I'm not giving you a number to plug into f?
Then you plug in the function.
You actually plug in the function. And so it tells me to take the function f, which is this guy, and everywhere in this problem there's an x value, you plug that guy in there. There's g. Everywhere there was an x in g, you're plugging in can't do that while it's taping. Never mind. Oh, now I'll have real funky. I don't know what's going on now. It got all skinny on me. All right. We good? It's all Sarah's fault. All right, so we plug in. There, it's back. Back to normal size. And so everywhere in the function you see an x, you take out the x and you plug in f of x. The biggest thing is remembering stuff like you got a FOIL. And that you might, if there was a negative 5 out here or something, you got to distribute to both of them. So in this case, it's just kind of straight up. Don't forget to FOIL, first outer inner last. Nothing needs to happen there. Don't forget the negative 1 at the end. People do that all the time. They get so concentrating on putting the stuff in for x, the minus 1 at the end, they just, because they get lazy, they don't write it on the second step, and then they forget about it on the third step. Boom. What you need?
What's the other thing where you can write it?
This notation?
Yeah.
Yeah, I'm never going to write it that way. So the thing that you have to be able to do later on, when it comes to us doing derivatives, remember derivatives back beginning of last year? When it comes to us doing derivatives, is you have to be able to recognize that a function is a composite function. Now, let me back up for a second and don't freak out here, backing up. If I gave you this, there's no way in the world you could recognize that as a composite function. You would not be able to recognize that I did that to it. But some functions you can. And those are the kind we're going to deal with. You should recognize this as two things put together. So write that function f of x as a composite of h and g. That makes sense? The outside function is the sine of x. And inside of the sine of x, I've substituted in 2x plus 1. So in that case, the outside function is h, and what got put inside of that function was g of x. That's a big deal, because, listen to this statement. The derivative of a composite function is found by taking the derivative of the outside, evaluated at the inside, times the derivative of the inside. Don't need to know that yet, but that's a statement you will know by heart. But notice what it involved. Derivative of the outside, you got to recognize which is the outside function. Evaluated at the inside, I need to recognize which is the inside function, times the derivative of the inside function. So I got to recognize, glancing at this, what's the outside, what's the inside, and then be able to take the derivative. The end. Say goodbye.
Bye.